All right, so now that we know what a vector valued function is, how do we graph a vector valued function? So we know from our last example that we're plugging in values of t and we're getting vectors as outputs. So we could kind of think of plotting points. I could plug in and say maybe it gives me this vector first, and then this vector second, and this vector third, and I could go through and I'm getting lots of vectors. And then maybe it even backtracks a little bit for the values of t. And I start getting this pile of vectors, and you could imagine that if I keep doing this, this is just going to look like a pile of sticks, and it's not going to be very meaningful. So instead of graphing the actual vectors, we're just going to graph the points that are the tips of the vectors and sort of trace those with a curve. And so if I do that here, if I can kind of remember the order that I got, went along here, and then it kind of curved back around here. Right? So this gives us an idea of how the vectors are tracing out as they go through the values of t. So we could even say it's going in this direction, at which point you're like, wait a minute, this looks familiar, right? This looks like when we would say x is defined by the function f of t and y is defined by the function g of t. This looks just like parametric equations, and it actually is exactly like parametric equations. All right, except it's going to be helpful for us sometimes to think of those parametric equations as the components of a vector, as the output being a vector, particularly in some physics applications. All right, so let's go look at a few of these vector valued functions being graphed by some technology. All right, so here I have a pretty cool website. I'm going to link this on our Moodle page so you can play around with it. You can see up in the upper right-hand corner there, it says function A, and I've got the X component function and the Y component function typed in, and it gives us this sort of funky shape here. And you can see it's got these vectors on there. So it's animating what's really going on with this curve, right? So it's just tracing out the tips of all of those vectors as it goes along. And essentially, again, this is just the parametric equations that would graph the exact same curve. All right, but we're going to think about with a vector valued function as each point on this curve being associated with the vector that attaches it to the origin. All right, so now that we know that vector valued functions and parametric equations are essentially variations on a theme, we can use what we know about parametric equations to figure out what the graph of a vector valued function might be. All right, so we know that this vector valued function is defining the x component with 3 cosine t and the y component with 3 sine t. Right? And if you think about that like a parametric equation, that should feel a little bit like a circle to you. Remember, x equals cosine t, y equals sine t. That's our unit circle. And we were very deliberate about this when we did parametric equations. If you want to go back and look at those, you can, where we would divide both sides by 3 and square both sides to figure out that this was the equation of a circle. All right? But essentially, this is taking the x and y coordinates of the unit circle and multiplying them by 3. This is a circle centered at the origin, just like the unit circle, with a radius of 3. Okay, so this is going to be a circle with a radius of 3 centered at the origin. All right, let's double check that with some technology. Okay, so here's our 2D vector valued function grapher, and we got 3 cosine t and 3 sine t typed in for the x and y components, and we see that perfect circle situated at the origin with all these vector valued outputs tracing out a circle with a radius of 3. All right, let's try another one. So this one's in R3, and we have the x component defined by 2 plus t, the y component defined by 1 minus t, and the z component defined by 3 plus 2t. All right, and when I write them that way, those should look familiar. Those look like the parametric equations of a line. Okay, so this is a line in R3. It's going to be through the point right here, 2, 1, 3. And remember that the coefficients of the t's give us the direction vector. So our direction vector is all the coefficients of the t's. It's t means 1 minus t in the middle and 2t on the end. All right, this last one's going to be a bit trickier. We're not going to know exactly what it looks like, but we're going to take a really good guess and then hopefully have GeoGebra confirm it. All right, so this one's in R3. You've got your x component defined by 2 cosine t, your y component defined by 3 sine t, and then your z component defined by t. So let's focus in on the x and y. All right, so this x and y components here, That looks almost exactly like what we just did in R2 with x equals 3 cosine t, y equals 3 sine t, all right, where it was taking that unit circle, x equals cosine, y equals sine, and sort of enlarging the x and y components. But this one is enlarging them unevenly, right? So we're multiplying the x component of that circle by 2, we're doubling it, but we're taking that y component and tripling it. Okay, so we're stretching out a circle a little bit in the x direction and a little bit more than that in the y direction. Okay, so that should feel like an ellipse, right? So if we graph an ellipse that's got kind of an x radius of 2 and a y radius of 3, all right, that's what this should be doing in R2. All right, we would start off, you know, like this. All right, so that's what the x and y components should be doing, tracing out an ellipse. So like we're looking over the xy plane here, but then there's this z component. So z, as t increases, like from 0 to 2 pi or something like that, the z component is just linearly climbing up. Okay, so the x and y components, as we look down on the floor for the xy plane, are tracing out this ellipse over and over and over again. But as it does that, the z component is asking the curve to lift. All right, so that's hopefully going to be graphing an elliptical spiral as we travel up the z coordinates. Let's go see if that gives us the right curve. All right, so here we are in GeoGebra, and I have our curve typed in, our vector valued function, x equals 2 cosine t, y equals 3 sine t, and z equals t. And let's see, let's turn this on and see if it looks like the spiral that we were hoping it would be. And there it is, it looks like it. All right, and look at this. If I look down from the top of the z-axis onto the xy plane, okay, this thing exactly projects onto an ellipse with an x radius of 2 and a y radius of 3. But then when we kind of stretch it out and let the t component grow, the z coordinate grow with the t, then it traces out this elliptical spiral. All right. So again, let me turn on this vector and let it go around. So there's the vector at t equals 0, so that's why we get that point there. And then as t grows, you can see it tracing out that spiral curve. And I'll link this one onto Moodle as well if you want to take a look at it. All right, so that's it for today for the graphs of vector valued functions, and we'll talk about taking derivatives of vector valued functions when we're in class together.